To talk to you about aerospace technology and architecture. Now, I'm not an expert in architecture, but I am a kind of an expert in aerospace technology. I just retired after 25 years with Rockwell, which brought you the Apollo project and the recent little old Space Shuttle flight. And I'm an engineer, and I have dealt with the kind of technology which is of application from space to earthly use. And I imagine that some of you have heard of some of the items, but you're going to hear a lot more this evening, and I intend to stay here until everybody leaves, because I have a story that takes a long time, but I'll tell it fast, and I'll show you a film, and then I'll give you some information that could make you wealthy. Okay? So the goal today is what? To find out what kind of aerospace technology you as architects might use. Number two, to get an insight into a little background on the Space Shuttle flight, where most of the newest space technology is coming from. And third, for all of us to get rich. Now the last part, the rich part, happens at the end, so you're going to have to hang in with me before I get to that part of it. I've been traveling around the country for many years giving talks to trade associations about the Space Shuttle program. And I have only had one other experience talking to a group of students. And the last time I talked to a group of students, they all stayed awake during the entire talk, which I cannot say the same for trade association people. So I'm looking forward to you being an alert audience and winding up being wealthy here at the end of the evening. One of the reasons that I even know Ray Cappy and Glenn Small, being an engineer in the aerospace industry, neither one of them is that kind of person. But back in 1959, I did work with a lot of architects when the City Building and Safety Department declared that the Simon Rodea Watts Towers were dangerous and apt to fall down. At that time, I was the engineer who did 100 pages of calculations, which were completely disregarded by the city bureaucrats. And then I did a load test on the tallest tower of the 99.5-foot Watts Tower that proved that they were in fact strong enough, and that is probably the reason that there's not a blacktop paving lot out there and that the Watts Towers are still there. But I met a lot of the architects that I know now back in 1959, before you were born, and that was 2 years after Sputnik. Now I could talk about the Wright brothers, but that's even before my time. In any case, I guess the most important fact to realize is that the space technology that's developed by NASA belongs to all of us. It's the only branch of the government that's worth a damn, really. I mean, I don't like the IRS, and I don't like a lot of the other bureaus in the government, but NASA, the National Space Administration, has in their 1958 Space Act the requirement to make the aerospace technology that they develop free to all of us. And that's unique. That's not true of the other agencies, like the Department of Defense or the Navy or the other branches. That means that the technology belongs to all of us, and NASA's requirement is that they get out and make it known as to what it is so that we can use it. And I'm going to tell you a little bit and show you some slides about how they do that so that you can then use the system so that in the last part of the talk on when we all get rich, you'll know exactly how to do it. I'm even going to give you the names and phone numbers of the people I call the radars. If you ever watch MASH, there's a guy named Radar, and if you want to get a pass to go here, you want to get a bomb or whatever you want, another cart for a patient, of blood, Radar knows how to get it. Well, after over 30 years in industry, I've learned that the most important thing is to find out who the hell are the radars, because they can save you months of work. You just call this guy or gal up on the phone, You say, I want this, and the next thing you know, it's there. Okay, I'm going to give you the names of the local radars that will be able to get you in touch with the technology that I will show you, so you'll be able to get a hold of it and actually use it. And that's another key to our getting rich here tonight. Now let me start out with a few slides that I made at home in my office. Being retired, I do a lot of work by hand. And here is hopefully the first slide. There it is. Okay, architecture and aerospace, what I told you is that the spin-off belongs to all of us, that NASA will help us, and I'll tell you who those people in NASA are, and that others may too, and the reason is it's the 1958 Space Act, which says that that's the way it's got to be. Now, when Rockwell won the Space Shuttle contract back in 1972, we were the low bidder. You know what the low bidder is, okay? We cut all the corners we could on when we estimated the job, and that's engineers and architects all have to make estimates. And what we did was we said we're going to use all of the existing technology which has been proven to be space-worthy, that would man-rated, that would be reusable. And we used the technology that came from the Gemini, the Mercury, and the Apollo, and the Skylab, and the Apollo-Soyuz test project. We used the same engineers that we had. They were much older. I mean, all of us were getting older, but they were the same engineers. We used the same subcontractors. We used a lot of the components that we had developed for the Apollo and the Apollo-Soyuz and the other projects. And that's why we were the low bidder. We did not expect to develop any outstanding new technology, because the new technology that we had developed, we thought we had already developed on Apollo. However, the clause, the new technology clause, which is the embodiment of the law of 1958, says that you will identify that the employees of these companies that get these contracts and the subcontractors will identify the technology and promptly report them to NASA, so that NASA can in turn make them available to us, the people. When we got the shuttle contract, our rule was don't do anything new and different. In other words, do everything the way we did before, and therefore you would assume that there would be nothing new developed. Okay? Well, needless to say, that was not true, or I wouldn't be here tonight. There were a lot of new things. Now NASA has a system that they use to capture this technology, and the system consists of technology utilization officers, that's TUOs, and that's a person assigned at each NASA installation. There's one at JPL here in Pasadena. There's one in Houston, one in Huntsville, one up at Ames, up north of California. There's one at Wallops Island. There's one in Langley in Virginia. There's one at Cleveland, at Lewis. There are 9 installations. They each have a TU officer. They each have a patent officer. There are industrial application centers throughout the country where and I'm going to leave some information here that you can use to go to those centers, and there's one here at USC, and actually get technical answers to technical problems that you may be confronted with. And the first time you go there, it doesn't cost you anything. After that, it costs you a minor amount of money for a computer search, and I'll talk about that a little bit later. NASA also publishes books called Tech Briefs and backup data called Technical Support Packages, and I'll get into that a little bit later. And then, of course, there are patents and the abstracts of patents, which you can see and look at, and you can use them. You can take them. They can be yours. You can pick up one of these NASA patents and use it and go into business and forget architecture and just, go build a widget or whatever. I don't recommend that, but you might want to do that. Now, in the contract that Rockwell got on the Space Shuttle, it said, although we didn't believe it, we had to do it. It said, NASA expects a large number of valuable developments to come out of the Space Shuttle contract. I already told you that we did not, because we thought we had done all the development on the Apollo and previous space programs. They also demanded that we have prompt documentation on these items. they also asked us to help our subcontractors, because NASA had had a very bad experience with their subcontractors on Apollo in receiving new technology reports from the subcontractor employees, because a busy engineer, I guess like a busy architect, really doesn't want to take the time to fill out a very complicated form after they have done their creative work, and fill in a lot of blanks. But in order to understand the inventions and the discoveries, someone has to go fill out a disclosure. And engineers hate to write. Most of them don't know how to write. I'm not sure about architects. Do architects know how to write well? Okay. No, yes, okay. Half of them do. But it's a tedious thing after you've created a new design or created a new configuration or whatever to go and explain it to someone. Here's exactly what I did. And I'll show you the form that we made these poor people fill out, and you'll know why no one wanted to do it. Furthermore, at Rockwell, the NASA demanded that there be a dedicated group of engineering people who would make sure that all of these things happened. And Rockwell is a very intelligent company led by brilliant people, also very successful financially. And in their infinite wisdom, they chose me to head up that unit in the engineering department to find all this technology, which I did for about 9 years before I retired. I think I see a funny face over there, a familiar face, sorry. Okay, as a result of the work that Rockwell did on the Apollo and the Saturn contract, we had reported about 8,000 or 9,000 disclosures. We call them TUs, technology utilization items. And that curve, which is not very straight, shows that over a period from 1962 to 1973, there were almost 4,500 from the Apollo program, another 3,500 from the Saturn program, and some 700 from other NASA contracts. So now, what are we talking about? We're talking about that's how many inventions and discoveries that are ours, all of ours. In other words, that's how many came out of the program up before the shuttle was started. So all those new ideas and many patents belong to us, okay? And I'll bet no one in this room even knew that before. Is that correct? Did you know that before? Okay, now aren't you glad you came? Okay, so that's what it's all about. We have all these very creative people who work on the space program who come up with these ideas. I now am going to show you a short movie, and I'd like to give a little introduction to it. I'm a member of everything, but I'm a member of the American Institute for Aeronautics and Astronautics. In fact, I'm the chairman of a group called Society and Aerospace Technology. And the role of that subcommittee is to do the kind of thing I'm doing here, is talking about the kind of technology that comes out of the space program which can be used by us other kind of folks. That organization had a convention recently in Long Beach, right after the successful flight of the Space Shuttle Columbia on April 12th through the 14th, which I'm sure you heard about or saw or whatever. I don't think any of you, well, I don't know, how many of you people watched any of the Apollo splashdowns? All right, very good, okay. Well, the shuttle is really an amazing vehicle. It weighed 200,000 pounds when it landed, okay? And that kid went all the way into Earth orbit, and for 36 orbits, 54 hours, with those astronauts, and you'll see them just having a great time, really. Now, astronauts, I met most of the astronauts over the years, and they're not like us at all. They're more like the motorcycle people, you know, or the skydiver folk. You know, they're really completely out of their minds, all of them. And we heard Bob Crippen and Johnny Young out in this Long Beach auditorium do a live dissertation on a silent movie. And I was lucky enough to get it for us all to look at. And you'll hear the ad-lib voices of Bob Crippen and Johnny Young when this movie was shown in Long Beach, they recorded it, and that's what I borrowed, and I have to get it back first thing in the morning. So if we can turn the movie on, and I'd like to talk and answer questions when I'm done with my whole talk, but I think you'll really enjoy this movie.
Okay, this is just background stuff, shows the vehicle on the pad. This shows Bob Crippen getting ready to fly, and there's me, and you can see my big project the week before flight was getting bigger United States flags put on our pressure suits. And the reason for that was one of these bureaucrats told me that it had to be a small flag to balance the Space Shuttle program, and I pointed out to him that the United States was bigger than the Space Shuttle program.
This shows us in the van, the traditional van that had been carrying Apollo crews out, that we rode out and going into the white room of the vehicle. Everybody had to wear those little masks, theoretically, for our last week there so that we wouldn't contaminate them or something.
They found that nobody at the cave got sick from us being around them.
This is shutting up the hatch just prior to launch, and that's John said it gets kind of lonely out there.
This is high-speed ignition of the three main engines. The vibration in the cockpit was very low at this time after the engines light off. The instruments just a little blurred, but you could read every one of them. Look at those babies come up to speed. This is from the cockpit. Shows how the vehicle moves back and forth there. And this is high-speed photography of the bolts blowing and the solid rocket motors lighting off. And all that is water spray right there where they're trying to keep things cool and not having much luck. And this is very high-speed photography, because when it lit off there was a couple of thumps and we started moving up very slowly. Look at these beautiful shocks coming out of the main engines at liftoff, and it's moving a lot faster than that. This shows how close it comes to the intertank access arm, which has always worried me some. It's really getting up and going.
John and I expected a real hard kick in the pants. There shows that what it looked like out John's window.
It called tower clear right from the cockpit.
But it was actually a really very smooth liftoff with very little shaking associated with it.
Watch it turn
There's
around.
There's the roll
there.
program.
See it rolling.
Head us out over the ocean.
Degrees.
And the vehicle is, the cockpit vibration is such that you can still read all your instruments in there, and maybe 10 cycles per second. This shows the roll program from inside the cockpit out the side window, and it's a thing of beauty. It's just as smooth as glass. There's no accelerations involved, and this shows the vehicle speed picking up. It's probably about ready to go supersonic right now, almost going straight up. And we said that's what it's going to do, but I didn't really believe it would, but it did.
We were getting a little loft on our trajectory here that we're still analyzing right now. Also, I was seeing some debris coming off from up over the nose that was coming back and hitting the windscreen and going over the top of the vehicle that we weren't sure what it is, like ice or Sophie. That's the stuff on the external tank that they're still analyzing.
I believe that tail is about 750 feet long, and maybe you can see it better from here, maybe 600-700 feet long, maybe 150, 200 feet wide. It's really impressive. I'm glad we couldn't see that.
Thank goodness for no rearview mirror. The ride was very smooth throughout this. Up in the transonic phase, it shook just a little bit. They're coming through max Q.
This is a camera inside the orbiter from the ET doors and shows the external solid rocket motor separation. Isn't that a spectacular shot? And then we show it again from inside the cabin, although the light is much brighter than this.
The big flash across the windscreen.
This shows it. We never saw these pictures, but here's the picture of separation outside from high-speed cameras. And isn't that terrific?
From onboard sensations, the only thing we really saw was the flash of light and our normal avionics cues that we had dumped the solids. We did not see them go away nor feel any jolts.
We're less than 1 G right after separation, transverse Gs, and this baby's just chugging along, and it's just as smooth as glass, that ride is.
Here you see some particles coming by John's window, a couple of white objects. There were one that was indicative of the kind of stuff that we've been seeing throughout the flight.
This is umbilical separation back in that view that we saw, and this is external tank separation, and it is a spectacular sight.
That white particles you see there are ice caused by the hydrogen freezing as it's coming out, and perfectly nominal.
There's the fitting that goes up in the orbiter. There's the umbilical plate, and there's the tank. And as you can see, all this black material there, that's the way the SOFI works. It chars and turns black. So it's a high heating area in there, and it really caught it. And there's another place that's sort of discolored up here toward the nose of the tank.
There was supposed to have been a tumble valve actuate to start the vehicle tumbling, and it did not work. And from our standpoint, it gave us a much better view of the tank. You'll also see the nose discolored.
It almost looks like the nose is it's got all the SOFI gone from it, because there's a sort of metallic color there, but that might be bright sun.
Yeah, we're not sure of that, and people are analyzing that still. This is a scene of me climbing out of the seat. All of the operations associated with the suit and the seat while you're in zero G are much easier to handle than it is down here on Earth. I'm just stuffing the helmet in a little bag along with the gloves so that we can tuck them away. There's quite a few connections associated with that suit, but it's no real problem to handle it all in zero G.
In 1G, we had a lot of problem with this helmet. It was always bumping into the hand controller and firing things. There, you see it's up there out of the way. We finally got it right.
Sets and floats nicely.
I'm not going to tell you this picture was made right after we got into orbit, because I don't think either one of us was that gutty, but we made it later on and then ran it backwards.
Actually, we did a suiting exercise while we were on orbit just to make sure that we could get the suits and get back in the seats with no problem, and that's when we filmed this. This is two TV cameras muxed together, one on the left and one on the right, shows the initial payload bay door opening. All of that went nice and smooth. You'll notice the ohms pod coming into view right here. This is the first time we saw some tiles missing off of the ohms pod.
You notice the door kind of hesitates when it opens, too. It did this in a fixture on the ground, and they told us, well, that was due to the fixture. That's the way the door really works.
The camera on the right is an aft camera looking forward. You can see the windows coming. The one on the left is a forward camera looking aft. That door operations went as smooth as it could be, which I was mighty happy, because I didn't particularly care about the thought of going outside and trying to do anything associated with them.
This is a view, panning the outside, that shows the radiators deployed out there. That's a beautiful, beautiful shot with the television.
You can also see those radiators when you look out your forward windows, which surprises us a little bit.
This is an ops mode 8 check out of the hand controller. You move it full throw, and then you read on the cathode ray tube, which is where I'm looking, to see if the hand controller is working properly. And this is very exciting. A little bit of this will last you about 6 months.
This shows a camera forward in the cockpit looking aft, and with John coming out of the seat. This was actually some TV stuff that we did for a status report. Pretty good indication of the kind of problems we have with some of our comm lines, which you had to work pretty hard to make sure you didn't get tied up in those things.
And we stayed tied up in them the whole flight. The government is now looking at wireless mics that I think will really improve the capability of the crew to operate. As you can see there, I'm having to hold mine next to my mouth so I can talk to people.
This is a shot down on our mid-deck storage area where we had all of our stuff stowed, and this was actually just after the press conference, or not press conference, after the conversation we had with the Vice President. Zero G is something else. That is something that all of you should have an opportunity to experience. It is really fun.
You know, if you could do that in your living room without breaking your leg, you sure would.
There's no problem trying to restrain yourself anywhere down there. I'm in the process here of changing out one of our LIO canisters, which is used to, that we run the air through to take out all the CO2 and any contamination. It's a very easy job. We had a couple of troughs down there where we stow LIO canisters, and you could just put your legs down in there and kind of push them apart, and it restrains you very nicely.
Look at this. This shows the mobility that we have down the mid-deck. People thought we needed restraint systems to tie ourselves down in there. You don't need any of that. Now watch this mobility that Bob has when he kicks off and goes up to the top side. Boy, I'll tell you, if that isn't the neatest thing in the world.
The thing about it is you don't really go flying around. You need to move a little bit slowly, otherwise you'll end up banging into something, but there's no problem controlling yourself any place you want to go.
Try that. Try that in one gravity and see where it gets.
You see, I just was wearing my socks there. I never put any shoes on while you're on orbit. I don't like to when I'm in the house either, so.
This shows what the television will show you out the window, and shows what a great view those spectacular windows gave us. Here's another television view of the Earth.
Now we're coming up to the reason I was glad I was flying with a guy like John that's got all the experience. We're getting ready to come home, and sitting beside a man that knows space testing like he does made you feel mighty good. We're shutting the doors, and all of that again went just like we wanted it to. There were no problems at all associated with it. You can notice there's a little bit of jerky motion when it comes down. We were lowering the starboard door down easy, and you'll notice it bounces pretty good, which we're having to pass on to other following crews to make sure that when they close it, they don't have any problem with overlap. Got it all tucked away, and we're ready to come home.
Now this had them stretch this picture because in the real world there was a beautiful pink up here due to the heat. This is the first part of entry, and there's the sunrise coming up. And we're moving along at about 300,000 feet, and we're just about to 265,000 feet where we go in our first roll reversal. And you'll see that pretty shortly.
Now we're moving pretty fast, but not quite this fast.
Yeah. That's the first roll reversal. And here's the second roll reversal. It's done at Mach 18.5, and this is at 2 frames a second. So we're moving 6 times faster than we would in the real world. 12 times maybe, yeah. Mach 18.5, and you really see those clouds go by even in the real world, but it's not quite this fast.
But you certainly.
The next roll reversal is at Mach 9.8. There it goes.
We did the roll reversal a little bit slower than that.
Yes. And here we come back at the 4.8 roll reversal, and that's Bakersfield out there.
Coming across the Hatchby in the Sierras.
That's Bakersfield right there.
And the vehicle sort of rolls rings level, and this is about at 80,000 feet, and then we went to real-time photography, which is only twice as fast as happens in the real world, and as you can see, everything is slowed down quite a bit. We're pretty high right now, maybe 75, 80,000 feet, coming across the lake bed areas that we told you all about. There's China Lake up in that area up in there, and you can see it out the left window.
There's Cuddyback at Pork Chop Lake coming into view at the top.
Right at the top. We're coming out to swing around the heading alignment circle, and it sure is a beautiful view. Looking out that window, you can see everything you need to see. There was just no doubt in our minds that we knew exactly where we were in the flight, even by comparing what we had on our normal ground track with what we're seeing on the instruments. There are 3 sisters up there.
The ride-in up to this point had been nice and smooth, and the vehicle controls really tight. It's a nice handling space.
Chase plane joint up there.
And we're getting ready to go in the turn around what we call our heading alignment circle. That's the Mojave River, which is mainly a dry lake bed or dry river bed out there. John is driving the vehicle at this point in time, and it really handled nice. We were right down the middle of the corridor all the way.
The remarkable thing about the Space Shuttle is it's all electric, and when you move the wings somewhere, they stay there. You put the nose somewhere, and it stays there. It's just an admirable handling vehicle. You couldn't ask for anything as responsive, and as for this kind of a job, it does it exactly like you want it to.
Couldn't have ordered a better day for coming back in. We could have navigated visually all the way from when we hit the coast, which was just a little less than Mach 7 up south of the San Francisco area, all the way down to the San Joaquin Valley to the Edwards. It was no problem knowing where you were at any time.
There's the highway it's north of Edwards there, and you swing across lake bed, and it's kind of hard to see at first in these films, but there's the old aim point right there. We're starting to come down the glide slope there. The runway's still hard to see there.
We have some aim lights that give you an indication of what your glide slope is out there that we refer to as PAPI lights. We also had locked onto a microwave landing system, and all of those ended up agreeing right on as to where we were, no doubt whatsoever.
Here's our old chase plane. He's flying back and forth across the bottom of the vehicle, taking pictures to see if there's any tile damage that would not show up. You know, they thought they might get some from the rocks and everything on the desert floor, so he's covering that right now. The chase plane did a real terrific job. The vehicle is very easy to control in this flight regime. We're about into pre-flare right now.
And I was flying about 285 knots at this point. We're like about a 20-degree glide slope. everything was just as smooth as could be.
It lands like a rock, incidentally.
There's, we're going into pre-flare, and this is how it looks out the window. You may be able to see 2 or 3 of those lights. 2 white lights is what we're looking for. There are 2 there. We start our pull-up now, and there'll be 3. You'll see the 3rd one come on. So we're on a 20-degree glide slope to pre-flare, which means we can only land right down here at the touchdown point. Here's the wheels coming down.
The wheels really snap down fast. They're much faster than what I anticipated them.
And there's a couple of big black marks you'll see coming up here pretty soon. There they are. That's the touchdown point, and here we go, boy. What a machine. It didn't know about that. It's supposed to land on the touchdown point.
But excellent. You should understand, John was not trying to touch down on the touchdown point. What we were trying to do was to find out what the real deceleration and touch down about on an airspeed, which was about 185 knots. And all of the ALT flights and this one ended up landing long, which looks to us like we have a little bit more lift capability than what had been predicted.
And we rolled right up here so Kennedy Space Center's recovery team could get a hold of us and hook the coolant up as fast as possible. We rolled into the runway intersection. We did that on purpose, so we hardly used any brakes on this rollout, and there's the vehicle sitting, and she is a beauty. That's, believe it or not, the weight of that vehicle right there is about right around 99 tons. I keep reading where it's 150,000 pounds or 80 tons, but that one right there is 99 tons. It's quite a performance thing to return from orbit with 99-ton spacecraft and get her back all in one piece, I think.
Right on. Okay. Incidentally, the second flight, called STS-2, is scheduled for September 30 of this year. And it will not only do the things that this vehicle did, but they have remote manipulator arms in that 60, those doors incidentally are 60 feet long. Those payload bay doors that open up the clamshells. And they will have some manipulator arms that will actually, are capable of and will put other satellites into orbit right out of the payload bay. It will lift them out and put them in orbit. It also can recapture other satellites that may be damaged and put them back into the payload bay and bring it back to Earth to be repaired. But that's not why we're here. We're here to get rich. And there's where the technology is coming from. Let me quickly show you some areas that back in 1973, right after we got this contract, we predicted that there would be useful new technology coming from on the shuttle. And I'm going to go very quickly. The fuel cell technology, these are energy systems, new technology about energy systems. From our fuel cells, from our lightweight high-performance batteries, from our auxiliary power systems, and incidentally, these subsystems are built by most of the large subcontractors to Rockwell. Sunstrand in Rockford, Illinois, Sperry in Phoenix, McDonnell in St. Louis, and all those other big companies. And energy monitoring and control systems. In addition to that, in the world of computer technology, where IBM, Honeywell, Intermetrics, and several other companies work on our computers, the data acquisition, processing, and analysis, monitoring and control systems, communication and data transmission, and incidentally, architects better start having dishes on the roofs of all the houses so that we can communicate all over the place. I mean, your own private dish, okay? And as soon as you design a house with one, I want it, because you really got to have your own satellite up there so you can do your own thing with your own, communication type system. In addition to that, access by remote terminals, including data banks, which came out of Shuttle. These are all the things which came out of Shuttle. Materials and processes, and there are quite a few. You can probably read them if your glasses are clean or eyeballs are good. I guess the message is there's a little bit of every technology that came out of the shuttle. The people that design the shuttle get into manufacturing problems, process problems. There are 28 technical subsystems. There's people problems, there's testing problems, there are management problems. Every problem that industry and the country has faced has been exercised by the shuttle people, management and labor. And in manufacturing, there are other significant developments that have happened, and I'll show you some slides on those here in a few minutes. Even in textiles, some of the materials that we use that are made out of some incredible cloth that will withstand very high temperatures. We use them for the thermal barriers to direct the flow of the air during the liftoff, the high temperature portion of the liftoff, and also on return to protect the control surfaces. They have knitted some incredible cloths that will have application in firefighting and other uses. Some already have. Okay. This first section, which is part of my 7-part presentation, is followed by the second section, and there I have some slides, and I'm now going to see if I can move up the stage without tripping. And get to this here. It says forward. Aha, it came on already. This is that very objectionable form that all the engineering people had to fill out. It, in great detail, they must say what it is that they invented and what is the title of it, get it signed and witnessed, what is it specifically, how important is it, what is the potential market, where can it be used in society. On the second page, a complete description of what it is, and then a whole bunch of references. Anyway, engineers and other people hate to fill that form out, and that was the problem in getting all the items reported. Let's see if I can figure it out here. Okay, the system of reporting went from the innovator on the upper left through an engineer in my unit to a review board, to me, you've now finished the top, down to the bottom on the left where we decided to report it to NASA, through our patent department to see if Rockwell was interested in developing the technology further, off to our packaging department, and then off to NASA, and then off to the people. The way the people, you and I, will be able to get this technology are through some books. I'm going to leave some here that you can look at later and any time you want. In the lower left corner is the key book. It's called the NASA Tech Brief Book. And in it, it describes each of the detailed innovations and inventions that come out. It's a quarterly book. It's free. You can subscribe to it and get it. I doubt if anyone here has ever seen one, but you really should, because there's some items of great interest in the field of architecture. The book in the middle is called Spin-Off 79. That's an annual book. There's a Spin-Off 80 out, and I'm about to get Spin-Off 81. And I was looking in my library at the office before I came over here, and I found some really outstanding evidences of NASA developments which are currently in use in your field of architecture to build large air-supported domes, to effect significant savings of energy, and in many other ways, new materials and so forth. And NASA has a team, a manufacturing application team, and a medical applications team, which has helped trade associations similar to the ones that I've been going to in picking up on some of this new technology and improving the quality of life and, incidentally, their bottom line profits for a lot of these companies by using the technology that came out of the shuttle and other NASA projects. The number of requests, I picked up this slide when I was in Washington, D.C. here last month, and it only goes to 1977 because it goes way off that chart. There were 100,000 requests for additional information on some of these items that were published in the NASA Tech Brief Books in '77. And Audrey Smith, who's the Technology Utilization Officer at NASA Pasadena, JPL, told me about 10 days ago that last year they had 100,000 requests just at Pasadena for backup data on their new developments. What NASA technology can do to you, for you, solve manufacturing problems, provide a base for new products. Now this is intended for industrialists. For us guys, later on we're going to find out how we're going to get rich on it. Okay, the team, the objective, of course, of these teams which are funded by NASA is to spread the technology throughout the populace who pays for the program. NASA has spent something like $60 billion on research and development in the last 15 years, and the results of that belong to us, and this team is one that tries to get it out to the people. The NASA Center at USC has an information retrieval outfit. I have brought with me a whole bunch of information which I'm leaving on the corner of the stage that you can look at when I finish talking, and you can actually use it to get real information that may be puzzling you in solving one of your architectural problems. This is still at USC, the NASA IAC, their Industrial Applications Center. You use their computerized searching technique. They do manual searching. They have technical coordinators at the various NASA Research Center, and then they have consultants who can help you. Okay, now I need some lights. Also need some water. You caught me. Okay, I'll go back to the other place. I figure if I keep moving, we'll get through this presentation. That was part 2. Now, in part 3, in order to inspire the innovators, the engineers who hate to write things out, we looked at a lot of systems. We looked at all the motivation programs, we looked at psychological programs, we looked at all kinds of things, and we decided that greed was the answer. So we use greed, we give them money, okay, for turning these items in, particularly the really good ones. And when I retired here in February of this year, a person who came up with a reasonable, good item would get a check for $50 immediately from Rockwell. Later on, they would get a check for $100 from NASA. If the item got applied for a patent, they would get $200 more from Rockwell. This is for the same item, which they did just in the line of their duty. They would also get another check later for $150 from NASA. When the patent issued, they'd get another check for $750 from Rockwell. And then if the item went into commercial use, they would get royalties, which could be a lot of money. Beg pardon? It would sort of depend on the thing, but it would be somewhere in the 10% area, I would believe. Somewhere in the 10% area. Yeah, I don't think it was written down, but that's how it came out most of the time. They were pretty generous, I believe. Some companies pat you on the back and give you nothing. In any case, the one slide I have, which I don't think you have to dump the lights for it. I've got one slide, and can somebody flip that on, or do I have to go around and do it myself? I guess I'll do it myself. This is a very free-form briefing here. There we go. There it is. This was one of the certificates that we gave out. And in addition to the good things, there were bad things. For example, in our contract with NASA, if we did not report an item, we were eligible for a $50,000 penalty. Okay? So rather than get the $50,000 penalty, we gave out the money to our employees to encourage them to send things in so we wouldn't get the $50,000 penalty. Rockwell's performance in the new technology reporting on the shuttle was so outstanding that they actually got additional award fee for their performance. So there was another thing that NASA did to Rockwell in order to encourage Rockwell to do it. Because really it's an onerous task. It's really an onerous task to write down your innovations and inventions. People just don't like to do it, and you have to really encourage them to do it. So if you're ever confronted with a situation where you have to get somebody to do something that involves writing, you better think about it plenty before you give them the assignment, because you're going to have to use the right approach and come up with some really clever thing like appeal to their greed, or you'll be unsuccessful. Okay. You sure have a neat place here running around in. The public benefits that have come out of the space program, and I mentioned some of them, are really overpowering in some ways. I heard an economist that works for the National Space Administration speak at a meeting that I attended recently, and I'm going to show you some of the things that he showed me. I'm not an economist, but he described the several kind of economists as macroeconomists and microeconomists. A macroeconomist is a guy who sits and looks at the entire economics of the country or the world, and a microeconomist is, I guess, when you and I are balancing our checkbook or something. That's the difference. But the macroeconomic look at the aerospace industry, from which these items come, shows that almost $12 billion was exported to other countries in 1979, which is the latest data we have, and only 1.6 billion was imported. So there was a net export of aerospace products of $10 billion. Now you probably, in reading the financial pages of the newspapers, the country has suffered for about 7 years in importing more than they export. Well, it sure as hell is not aerospace. It's other things. It's oil. It's, other products. But aerospace industry is a great contributor to a favorable balance of payments. The sales of the aerospace industry in the same year were $45 billion. That's in the United States and also overseas. And of that, almost $8 billion of the 45 was what they call non-aerospace product sales. And that's the spin-off. That's the developments that came out of the aerospace work. They wound up having some other customer than aerospace. So it shows the large value of these inventions that we're going to get rich on. There's a lot of money to be made. Until he showed me that, I wasn't sure, but this convinced me. Now in the microeconomic scale, the macroeconomic scale, they say that a dollar spent in technology, aerospace technology, will return to the country $2.6. That's called a 2.6 to 1 economic cost-benefit ratio. That's that number right there, 2.6 to 1. It's at least that. Some economists say it's 8 to 1. When you look at 4 specific developments out of aerospace: integrated circuits, cryogenic insulation, gas turbines, and a certain computer program which you may have used yourself called NASTRAN, the NASA Structural Analysis Program. I don't know if you know about it or not, but it's been used to analyze large shells and other structures, bridges and buildings and automobiles, and a lot. It came out of the National Space Administration. Those 4 specific developments showed a favorable balance cost-benefit of $7 billion. Now that was in those 4 specific areas, and of course there are many others. And the NASA publication program, the Tech Brief, which I'm going to show you later, showed a 6 to 1 value. It's a very low-cost program. They publish these items, people pick them up and use them, and it's worth 6 times more than it costs the government. It's worth to us 6 times more than the government spend on it. The bad news is that in patent trends, I hope you can read these, in patent trends from 67 to 77, the number of patents in missiles and space is down by 1/3 from what it was in 67, whereas in aircraft it's up 36%. And why is that? Because after the successful lunar landing, the government and the country lost interest in the space program. And the interest has been lost in the space program until, I guess, April the 12th, when the shuttle flew. The budget of NASA today is still much less in dollars than it was in 1968. And the dollars are worth about half. So that in effect, NASA has been operating on a budget about 1/4 of what it had been. When you think of all the new technology that comes out of the space program and the fact that we're spending 1/4 as many 1980 type, 81 type dollars as we did before, you really wonder where our priorities are. Because we're losing a lot of advances, and the last item shows that foreigners are owning U.S. patents at a rate 2/3 greater than it was in 1967. So what's happening? What's happening is the United States really gave up on spending money on the space program, and the foreign nationals now own U.S. patents in missiles and space that are going to bite us pretty hard, and already are. You may have heard of the French Airbus, which is moving in on the Boeing airplane sales, and things like that are beginning to happen. Incidentally, the number of NASA employees is now 1/3 less than it was 10 years ago also. So if you want a career at NASA, forget it. It's not a very neat place. Here's those numbers. In 1960, there were 10,000 NASA employees. In 1970, 31. There are now 22,500. Okay, there's some hope on the horizon as far as the aerospace technology transfer. There's a Public Law 96-480, which is called the Stevenson-Weidler Technology Innovation Act of 1980, which does provide some more services like I'm giving you, talking about aerospace technology, to architects so that you can understand what's available and how to get it. And that bill, if it's funded by the Reagan administration, and it may not be, could provide such people at the different federal laboratories to transfer the technology to the public. Another bill would establish an organization like the National Science Foundation, only called the National Technology Foundation. It's a bill that's up for a vote soon, called House Bill H.R. 3749. And I have a copy of these bills if you want to look at them. But the real outstanding public benefits that came out of the space program were the mission results. And I'm going to get to those here in a minute, but I will move back to center stage carefully. I don't know who choreographed my act here, but I'm sure moving around a lot. Whoops. Am I going reverse? Oh, I was hitting the reverse button. Sorry. There we go. I showed you before that we did not expect much new technology to come out of the shuttle. Well, we were wrong. There obviously was not as much as came out of the Apollo program. This dashed curve that goes up like a mountain shows the almost 5,000 reportable inventions, thank you, that came out of the Apollo program, and this solid line shows the shuttle reportable items, which at this point was about 2,000 through about a year ago. The first flight date, November 80, was wrong. Actually, we flew on April 81, but this slide was made before they extended the launch dates. So that's how many items, about 2,000 innovations came out of the shuttle orbiter contract at Rockwell and at its subcontractors. And I have the names of all those items, and I know many of the innovators and inventors personally, since I processed most of those items. There were some 1,000 items were submitted by Rockwell and another 1,000 approximately by the subcontractors. 450 as of a year ago were published. And 49 were going through some kind of patent action. So there were like 49 inventions that came out. The subcontractors curve below, the top curve is the Rockwell submittal curve from 1972 when we won the contract through the middle of 1980. About a year ago, and the subcontractors started slowly because we had to threaten them to get them to perform, and we also had to give them additional award fee. Now, the things that are a benefit to urban planners and to farmers and to state government people are the mission photos that are taken from the Landsat satellite series and the NOAA satellite series and others. And I brought along a few slides that I stole from NASA headquarters to show you, and they are showing in this particular case the large area crop inventory experiment from Landsat, and that's in one of the books that I have here, and you can read more about it. But by looking at this, they predicted that they could estimate the exact amount of wheat crop in the United States and Russia. Well, in Russia they came out within 1%, but they couldn't even come close in this country by using this technique, because our wheat farmers don't grow the wheat in nice uniform plots like the Russians do, so it's hard to spot it. But it was an interesting experiment. This is a study of the type of soil and pine and other growth in the Navajo Indian area. This is a shot of Georgia where they're looking at the shellfish production by studying the ocean, the color of the ocean, and they're looking at the environmental planning. And down at the bottom of this chart, and you can look at it later after the lecture, you can see that they have graded it in many ways from these really outstanding shots that they take from the Landsat. This is the Texas Wildlife Study, which is was along the Gulf Coast near Corpus Christi. And you can see the difference between the urban area at the top and the rural area just by the color. This is the Pacific Northwest program in the Portland, Oregon on land use study, and it covered some 10 million acres. And you can differentiate between residential, commercial, open land, agriculture, forest, and water by the different shades of color. And this was an interesting geological study. They enhanced this particular shot on the left. On the right, they could actually see the granite intrusions and some different rock strains. And this was done in Saudi Arabia. The last shot is one done in Texas near Austin, and was done with a multispectral scanner out of a Landsat image on a 13,000 square mile area, and I can give you more data on that. I just want to show these are mission items. That was the mission of this spacecraft, was to actually get these kind of shots that can be used by you people. Okay, now this is not a mission. This is a very clever innovation that came out of a subcontract on the space program, where Ball Brothers company developed a spray to treat the brushes on motors. They also found the same spray would handle the grooves in records. And you can go down to your record store and buy this incredible material called SoundGuard, and it will improve the life and the sound on your records. And it was what we call a spin-off from the space program. And that's exactly what this is, a spin-off. And that's what we're going to get rich on here in a couple minutes. We're going to get rich on the spin-off of the space program, and I'm going to do it all in 15 minutes or so. Okay, some of the spin-off that I want to talk about, I got to go down there. I guess if I were Superman, I could leap. Back here. There's a book, and here it is, called Space Benefits. It's put together by the Denver Research Institute. And in this book are documented thousands of valuable technology that are in use as a secondary use, like the coding on the records, okay? I've got some slides I'll show you too. But I looked through this book, and there's only one that says architecture. And it says, I'll read it to you. Geodesic Structure Design Program. Apparently, you probably all know about it, right? Developed for NASA headquarters by R. Buckminster Fuller, and I've heard of him. I know who he is. At Southern Illinois University, computer program used by Space Structures International Corporation, formerly Dome East Corporation, to design commercial geodesic structures. So apparently the computer program that was used to design some other space-type hardware was also used by Bucky Fuller on these buildings. In addition to that one, I found a couple others in my library before I left. I want to share with you, that you may know about, maybe not. These are two of those spin-off books that I talked to you about, and we showed and so these are beautiful books. You've got to have one, and they're sold by the government printing office. And I'm going to leave them here so you can look at them afterwards. But here's one. It says, A Roof for the Lion's House. And this was a space development. I should have had a slide of this, but I don't have one. That the Detroit Lions the new Pontiac Stadium has a domed air-supported fabric roof, and the material, beta yarn coated with Teflon, is the material. There's a space material that's being used by your friendly Detroit Lions, none of whom weigh less than 280 pounds, I think. There are also pictures of the University of Santa Clara, which has used aerospace technology to design to me, a beautiful looking building. Maybe you don't like it, but it looks good to me. The University of Florida at Gainesville has an outstanding building that also used aerospace technology in their design. A tension structure, which maybe you can see here, that I wish I had a slide of, at Laverne College, Laverne, California. Okay, and it says here that the fabric structure, the campus center, it's not air supported, but it used computer analyses from bird air structures, which came out of NASA. I mean, the program did. In any case, these books are just full of, when Ray Cappy and I first spoke about this, I thought, I'm going to have a hell of a time finding things in architecture that came out of the space program, but I didn't. It was easy. There's lots of them. And here is a highly reflected insulating material that you've got to put on the windows of the houses that you design, because it's very energy efficient. Highly reflective coating that came out of the space program that's here in this book. So there are a bunch of those items that are already in use, but we're not going to get rich on these We got to come up with our own things, and we're about to do that now. Are you all ready? Everybody want to stand up and stretch, and then you'll be ready to become a millionaire? Okay, because I'm about to really tell you what they are and how to get them. I guess first I had to tell you, where you can go to get help. I told you that you got to know who the radars are, okay? I don't know if you take notes. Do architects take notes? I know you make drawings. Okay, there's, I mentioned his name before, there's Audrey Smith, who's a very nice gentleman. Spent 12 years, he's an engineer. He's the Technology Utilization Officer at NASA Pasadena, JPL. He's a Purdue graduate like I am, and his job is to help us to get the technology and use it. Us architects. I now have become one of you, right? I've been here long enough. And Audrey Smith, whose phone number in the 213 area is 354-4849, has got to help you, or he's fired. I mean, that's his job. I mean, that's it. You know, if he can't help you, then he's through. That's it. So Audrey will be glad to help you to find what you're looking for in the technology to solve your problem. Is it an adhesive or a shape or a form or a, what is it? What is it you're after? You call him up and mention my name, and if he doesn't come through, you call me back and tell me. I'm in the book, the LA directory, Bud Goldstone. Okay, another one that can help you, and incidentally, NASA Pasadena office is at 4800 Oak Grove in Pasadena, in case you didn't know that. That's the address. It's Pasadena 91109, so you can even drop them a line. There's a man at USC whose name is Dr. Robert Mixer, and Bob Mixer heads a NASA-funded team whose job it is to do what? To transfer that damn technology, baby. And he's got to help you too. Bob Mixer, M-I-X-E-R. And tell him I'll get him if he doesn't. And his number in the 213 area is 743-6132. So there are two radars for you. They know where it all is. Now, it could be a development that came out of NASA Lewis in Cleveland or NASA Langley in Virginia. But they know, what's going on in the federal laboratories, and they're the ones to contact to get the help. Okay? There's also if you want to be a small business person, almost said man, small business person, there's the SBA, Small Business Administration. They have a program called their Technology Assistance Program, where you and I can fill out a form and they can go get us the solution to our technical problem. And now I brought this form along, and then I noticed it's got Jimmy Carter's picture on it. And he's not the head man anymore, but I guess the SBA is still there, and they still have this program. And that's another way to get help in new technology that came out of the space program, because the SBA helps NASA to get their technology out into general use. So I now gave you 3 radar folks, okay? Audrey Smith, Bob Mixer, and the SBA. Man's name is Noel Stimson at SBA, S-T-I-M-S-O-N. And the phone number is right on this thing here, I think. No, it's not. But I have it in my book. His number is 688-2946. That's Noel Stimson of SBA. And I know him too. All these people belong to an organization called the Technology Transfer Society, of which I am also a member. And that's our society does, is we are involved in the transfer of technology. Okay? And so that's a whole cult that you never heard of before. Just like you maybe never heard of some of these programs, but it exists. Okay, so now you know who they are, and you know what some of the mission developments have been, the satellite pictures for all sorts of earthly use, and some of the spin-off items. And I'd like to talk about a couple of really gee-whiz things, and I think I'll use some slides to do that, which means I have to go back up here. Water. Okay, maybe I'll hit the forward instead of the reverse. Aha! That's the end of a wire. And when we got the shuttle contract, we had some very stringent requirements on all the wiring connections in the vehicle, because when we stripped the end of the wires off to connect two wires together, we did not want to ding the conductors, make a crack in the conductors when we stripped the end of the wire off to make a connection. There are two kinds of normal wire strippers, mechanical and thermal. We invented a handheld laser wire stripper that will probably become a $100 million a year industry for somebody very soon. There's several large companies working on it. Down in our manufacturing laboratory, we developed the machinery in order to eliminate mechanical contact with the wire, like with the thermal and mechanical strippers, to narrow the width of the edge of the cut where you take the slug off the end of the wire, to cut the insulation, to strip it in less than a second and a half each job, and not to affect the metallurgy, which we accomplished with this incredible little gizmo where you you push the wire in this end, there's a rotating head goes around in a second and a half, and you pull it out, and you not only still have your fingers, but you've got the end of that wire stripped off in a very clean fashion. The entire installation, with my friend Floyd Urian standing here, consists of the stripper, which he's holding in his right hand, suspended by a counterbalance up there, and all this cooling unit and other material is just lab-type equipment down here. The stripper is in his hand. But that device is not in production yet, but and there's several large companies looking at it, but you just mark my words, in a matter of years, you'll have some of these that you can even put in your garage and use. A handheld laser wire stripper. Here's another device. This little power factor controller was developed at Marshall Space Flight Center by one of their engineers, a NASA engineer. And it looks like that, and that's the United States quarter there. And several companies are making this right now. One of them is a local company called Nordic. I talked to their sales manager the other day, and he says they're selling thousands of these each month. The unit goes from $5, which you can plug into a typewriter, up to $1,500 that you can put into a three-phase induction motor. It can cut down the energy use by 70% under certain loading conditions. They're now beginning to build it in as an original equipment into some of the induction motors. And this thing just took off. Like, there are now, I think, 100 and some companies that are building this device. And you and I can do it too. And if we can bring the cost down, we can sell thousands of these every month at $1,000 a piece. And that's a lot of money, okay? And it's free. Anybody can get the use to that patent. It's a government patent, and any of us can get the rights to that patent on that power factor controller. The NASA JPL people are working on robotics, okay? That's the use of robots to do things that are tedious for people or maybe too difficult to handle. And they have developed a computer and a robot system with a beam source that will perform perfect welds over and over and over again, which people can't do. And robotics and architecture, I'm sure there's some kind of a connection. And if you want to learn about that, you call Audrey Smith out there at JPL, because that's where they developed this system, which no one is using yet, and it belongs to you and me. And if you want to be, into it, call him up and tell him, and he'll take you through JPL. And call me up too, because I'd like to go over there myself. I'm ready. Okay, now the last part of this presentation is when we each get a chance to pick the exact method we want to be rich. Like, what is it you really want to develop? And I've got a listing here, and I'm going to stick around for a while after this, of a whole bunch of developments that are not currently being used by anybody, to my knowledge. And therefore, if you want to use them, you can develop these or use the technology, get the information, and use it for your own purposes. And I hope you can read these, because I don't want to have to read them all. Okay, I'm gonna change the chart from time to time, because I've got a whole bunch of them. There are 2,000 developments that are available for you that came out of this shuttle work. Okay, and if any of them turn you on, I can tell you how to get an exact copy of what that item is, so you might use it in your work in architecture. Right. Okay, I sold a fastener for a sandwich panel. Do I hear an offer on something else? You're right. A lot of these are, there's actually a fastener that we have, and that fastener was R&D. In other words, we just built a few because we didn't sell 1,000 shuttles. We sold 5. Okay, so there's just 5. There's no production contract. If you want to go into production and sell that fastener to put up panels in buildings or whatever, it's yours. It's yours. That man over there just got that. Okay, I'm going to change the chart to another one now. Here's some more. When you think about the space program, you think about all kinds of exotic, glamorous type things, but man, what were we doing? We're putting together metal, and we're putting together hydraulic systems and pneumatic systems and computer systems, and it's just like, like everything else down here on Earth. The vehicle will fly, but that's because we've got one hell of a booster under it, and a pair of wings to help it land with. But the rest of the systems are pretty straightforward. There's more. You like a pencil sharpener clamp, huh? Third one from the bottom? Drafting ink dryer, right. Boeing seemed to be confronted with some amazing problems. Their 747 is the what they call the ferry vehicle for the shuttle. You probably all saw the cartoon in the LA Times where it showed the mated shuttle and the 747, and the caption was, "Not tonight, honey, I'm too tired." I think that was one of the funniest spacey type cartoons I ever saw. Okay, I've got one more. Actually, I've got 30 more, but I ran out of time. I'm not lying. What's the question?
Space Shuttle RCS consumable?
Okay, RCS is a reaction control system. It's a little jet-type engine that goes and rotates the vehicle for, for attitude control, pitch, yaw, roll. There are sets of them on the vehicle. I left out part of my conversation in the beginning. I usually say that aerospace engineers normally can't communicate with anyone because they have a different language. And aerospace engineers just can't talk to people. They're really not people anyway. But I left that out. I left that out of this talk because I figured architects have their own language too, and you'd get angry with me or something. I'm sure you have your own language also.
We can't communicate with each other.
Well, we can't either. We got lots of different kinds. Anyway, I have really appreciated your attention, and I've enjoyed giving this presentation. And I'll be willing, as I said, I'll stay here as long as you want to, but I guess the class is dismissed, but I'll hang around. Take this off.
Can you actually get listings of computer programs?
Yes, I'll show you. I gotta return all this hardware here.
Everybody return the stuff here, okay? That way we can put it up here in the library.
Superintendent of documents, U.S.